All right, so let's talk about LeChatelier's principle. It's determining which way the reaction is going to go. If it's at equilibrium and you do something to change it, you do something to a reaction that is at equilibrium, it's no longer going to be at equilibrium. This is not going away. Through chapter 19, all the rest of the chapters have some reference to LeChatelier's principle. So you have to think conceptually. If you are not an abstract thinker, this is not going to be the easiest thing for you. I'm not an abstract thinker, so it took me a long time to do this. So I'll try to teach you how to think about it analytically, but it's not going away. So you can change concentrations, you can change volume, you can change pressure, and you can change temperature. So we're going to talk about how that makes a difference. Okay, so if you have a reaction that's at equilibrium and you change the concentration of either the reactants or the products, the equilibrium is going to shift away from the side with the added chemicals, or it's going to shift toward the side with removed chemicals. This is a graph. I don't like this graph. It tends to make things more confusing for me, but when you're dealing with concentrations, just remember, think about your reaction. So here, this is the radical reactant, here is the product. So in this generic, or it's not a generic reaction, this reaction, equilibrium constant is NO2 squared over N2O4. Now, if we add N2O4, think about it. If say we have 1 molar and then we make it 2 molar, this goes from 1 to 2. Does K get bigger or smaller? Well, it's not actually K, it'll be Q. It's gonna get smaller. Okay, so when Q is less than K, the reaction goes forward. So if you want to think about your reaction, write your equation. We add more reactants. Well, hello, it's going to get more products. If we add more products, it's going to go back to reactants. So that's how I kind of think about it analytically rather than spatially. But if you like the graph, go for it. So here, if you would rather just memorize a list, here it is for you. If you increase the concentration of 1 or more of the reactants, that means Q is less than K, which is what I just said. So the reaction shifts to the right or in the direction of the products. If you increase the concentration of a product, Q becomes greater than K, so it is going to move to the left in the direction of the reactants. Now here, if we decrease concentration, so like if you have gases and you remove some gas, that's generally when you're going to encounter this type of situation in a gaseous reaction. You decrease the concentration of 1 or more reactants. Q is bigger than K. So we took away reactants. We need more reactants. So the reaction goes left in the direction of the reactants. Who thinks this is extremely confusing? Nobody's going to admit that's awesome. It's because I'm fabulous at explaining it. Maybe not, but. All right, last one of the 4 here. If you decrease the concentration of the product, guess what you need more of? You need more products. If you take some products away, you need more products to get back to equilibrium. So Q is less than K. Reaction goes to the right of the products. Yes. I find it easier to either put this in terms of the equilibrium constant and think about Q and K, or to look at my equation and kind of put pluses and minuses and go, oh, I took some away, I need more of that. I added more, it's going to make more. But now, here in these situations, we're adding or subtracting concentrations. K does not change. Okay, so just make sure that the value of K does not change here. Now, volume and pressure changes. You won't see these that often, but we'll talk about it. This is going to be one you'll see a lot more often, and temperature is going to be one you're going to see more often. So you have to think about a container here and think about like a piston situation. So if you're pushing down or relieving. So if you decrease the volume, what happens to pressure? Pressure goes up. Yes. Or if you increase the pressure. Volume pressure. Boyle's law. Inverse relationship. All right. So if we increase the pressure, the reaction is going to shift in the direction that has the fewer moles of gas particles, because it wants, when you have less space, it's going to say, oh, well, if I shift to the side of the equation it only has one molecule versus two, it's happier. One molecule occupies less space in the volume than two. In general, that's kind of the principle behind it. I don't really like these situations. I have to think about them very, very hard. If you increase the volume, what happens to pressure? Decrease the pressure, yes. So either one. So if you have more space, the reaction is going to want to have more gas particles. It has to do with partial pressures. I'm not that big of a fan of it. Now, if you have a reaction where it has an equal number of moles of gas on both sides, then a change in volume or in pressure, is it going to make a difference? No, no. If you have an equal number of moles on both sides, no change. No change. I like that one because it's easy. And then there's also a similar situation if you add an inert gas. Inert meaning a gas that's not part of the reaction. So it's not going to react, it's just something else you're putting in the container. To the mixture at a fixed volume, it's going to have no change or no effect. It'll affect partial pressures, but it does not affect the ratio of the reacting gases. Again, not going to see this very often. Temperature change. I have to think about temperature change in a little bit of like a two-step process, but this is going to come back. On these, I told you K does not change. If you change the temperature, it will also change the value of K. K, your equilibrium constant, will change. Because if you go back and review the definition of an equilibrium constant, it's the ratio products to reactants at a particular temperature. So you change the temperature, value of K does change. So when you're evaluating this situation with a temperature change, you have to decide which way the reaction is going to go and what happens to K. So there's two things you have to figure out here. So for an exothermic reaction, let's review. Exothermic reactions release energy. We know this. We learned this in Gen Chem 1. Not that hard. So it will help you out if the problem says this is an exothermic reaction. Write heat into your equation as a product. Heat is a product.
When releasing energy is exothermic?
Yes. Delta H is negative, if you like the thermo concept. All right, so now, when you increase the temperature, are you adding or subtracting heat? Adding heat, yes, you're making it warmer. So you are adding heat. So this is an exothermic reaction. Heat is a product. If you add heat, it is the same thing as adding something to the product side. So the reaction goes this way. Now, so you're going to have a lower concentration, lower ratio of products to reactants, so K is smaller. Because if you consider heat as a product, you're going to have more products to reactants, so your ratio is going to go down. Still with exothermic reactions, if you lower the temperature, you are removing heat. Heat is being transferred to the surround, or yes, transferred to the surroundings. Okay, so you lower the temperature. So if you take heat away, heat is a product. You take it away, the reaction wants to go this way to replace heat that's lost. When heat is a product, you're going to have less products, more reactants. You're going to get K is larger because it really wants to form more products. It wants more products. K is bigger. Endothermic reactions, everything's the opposite. Endothermic reactions, everything is opposite. In an endothermic reaction, endothermic reactions absorb energy. So on your reaction equation, heat is a reactant. So if you raise the temperature, you add heat, heat goes on the reactant side, you get more products, K goes up. If you remove heat, heat is a reactant. You want more reactants now to replace the heat that's lost. Reaction shifts left, K goes down. It's a whole lot of conceptual mental gymnastics.